Okay, I welcome you all to my video lecture presentation. Myself C. Ashok Kumar, Professor, Department of EEE. And my course name is Electronic Device and Circuits, and it is Unit 2. The title of Unit 2 is Diode Applications, and topic for today lecture presentation is capacitive filter operation and derivation of ripple factor. The overview of my presentation goes on like this. First, I will be discussing about the types of filters, and I will be discussing about capacitive filter operation, and also I will be deriving the ripple factor of capacitive filter, and finally I will be recapping the things whatever happened. And the textbooks referred are, first one is Electronic Device and Circuits by Jacob Millman, and second one is Electronic Device and Circuit Theory by Bollisted and Neshelsky, and third one is the Electronic Device and Circuits by Salivahanan and Suresh Kumar. So first of all, what do you mean by a filter? Why you go for a filter? If you observe the rectified output, as you can see here, this is a rectified output. Rectified output will be looking like this. As you can see, it is a pulsating DC, which is not a pure DC like this. The rectification process means it has to convert AC to DC. Okay, but what is happening, if you observe the rectifier output, as you can see here, it is a pulsating DC, it is not a pure DC. Pulsating DC in the sense it contains both AC components and DC components. Actually, we expect only DC components to be present in the rectified output. But what is happening here? It is a pulsating DC. Along with the DC components, some AC components are also added. So that's why a need is there for us to minimize the AC components that are contained in the rectifier output. So that particular function will be done by the filter circuit. Filter circuit is an electronic circuit which is used to minimize the AC components that are contained in the rectifier output. AC components, in other words, we can call it as a ripples. Okay. So if you want to minimize the amount of AC components in the rectifier output, we need to go for a filter circuit. So that's why here always the input to the filter is a rectifier output like this. It is a pulsating DC, and the filter output must be look like this one, like a pure DC. Okay. So this is about the filter. So if you go for the classification of filters, basically 4 types will be there. First type is a capacitive filter, and second type is an inductive filter, and third type is the LC filter, combination of inductive as well as capacitive combination, and fourth type is a pi filter. As you can see here, the elements are arranged in the form of a Greek letter pi. Okay, so these are the 4 types. So first type, let us discuss about the first type. First type is a capacitive filter. As you can see, if you observe the circuit here, a capacitor is placed in parallel with the load resistance RL. If you observe this circuit is nothing but a full wave rectifier. Okay, full wave rectifier, this RL is a load resistor across which I am connecting a capacitive filter. Okay, so here this is the capacitive filter arrangement. Okay, and if you observe the inductive filter, as you can see here, the inductor is placed in series with the load resistor. Whereas if you observe the capacitive filter, here it is connected in parallel. Okay, and third type is, which is a combination of L and C, and fourth type is, once again, it is a combination of L and C, L, C1, C2. It is arranged in the form of Greek letter pi. So if you observe the output waveforms for capacitive filter, it will be looking like this. Actually, the pure DC signal will be looking like this. Okay, pure DC signal. But if you observe here, the capacitive filter output, whenever you are placing a capacitive filter across the load resistance RL, so the output will be looking like this. Simply it is shifted to a DC level and a ripple is sitting over it like this. Okay, so somewhat it is a better version when compared with the pulsating DC. The pulsating DC will be like this. Okay, so in which more number of AC components are contained, I am minimizing the AC components by going for a capacitive filter, and my output voltage will be looking like this. As you can see here, a DC level, it is shifted to a DC level, and some AC components are still sitting over it. Okay, so that is about capacitive filter. And if you observe the inductive filter, as you can see here, this is the output of inductive filter. Output means the voltage across the load resistance RL. As you can see here, inductor is connected in series. When this happens, the output is once again a ripple shifted like this. Okay, and if you observe the LC filter, it is a better version like this when compared with either capacitive filter or inductive filter. Okay, and if you observe the fourth type of filter, as you can see here, uh, the capacitor and inductors are arranged in the form of a letter, Greek letter pi. The output is the better version when compared with all the filters. It is the best one. Actually, pure DC will be like this. And if you observe the output voltage is somewhat closer to the pure DC output voltage. It is closely approximating the final DC signal. So these are the four different types of filters, but in our syllabus we are limited only to capacitive filter and inductive filter. So now let us uh, move to the capacitive filter. So this is a circuit diagram of a capacitive filter, and this is a basic diagram of the full wave rectifier. As you can see here, two diodes D1 and D2, and here a load resistance RL is there. Across I am connecting the capacitive filter C. Okay, and whatever the voltage that is developed across RL is the filter output. Filter output is nothing but that is output of this capacitor. Okay, so here the input signal is entered, which is an AC signal, and the output voltage across RL is a DC output voltage. Okay, rectified output is given to the capacitive filter. If you observe the output here, this is a rectified output. Once again, that is provided to the capacitive filter. So from rectified output, that a pulsating DC, you will be getting a better version of the output voltage, which is closely approximating the DC signal like this. So somewhat like a ripple is sitting over a DC shifted level. Okay. So if you observe the operation here, as you can see here, mainly the output voltage here EDC is nothing but the voltage across the capacitor C. The output voltage EDC, it is nothing but the voltage across load resistance RL, which is nothing but the capacitor voltage. Okay, so the capacitor charges whenever the diode D1 is forward bias. Okay, whenever diode D1 is forward bias, what happens here? The capacitor C will be charged in order to reach the peak value of provided input voltage. Okay, so whenever the diode D1 is reverse bias, the capacitor C will be discharged. So charging of capacitor happens when diode D1 is forward bias, and discharging of capacitor starts whenever the diode D1 is reverse bias. Okay. So during the positive half cycle, what happens here? The diode D1 will be forward bias. The diode D1 will be forward bias, and the capacitor C will be starting the charging in order to reach the peak value. So here, before going into it, so here I am drawing the rectified output voltage, which is a pulsating DC like this, as you can see here, based on which we can explain the operation. So like this. Okay. So whenever the diode D1 is forward bias, as you can see, this is a positive half cycle and this is a negative half cycle, 0 to pi and pi to 2 pi. Okay, both in the positive half cycle as well as negative half cycle, output voltage will be defined for a full wave rectifier. That's why, as you can see here, this dash shaped waveform is nothing but a pulsating DC output voltage for a full wave rectifier without capacitor, right? So here During the positive half cycle, this diode D1 will be forward biased and the capacitor C starts charging like this. Okay, it charges up to the peak value here. So the peak value, let it be EM. So it will be charging up to EM, right? And it holds the charged value. So assume that the value here is the during the positive half cycle, it will be charged to reach the peak value. Peak value here is EM. Okay, this is EM, right? So it will be charged up to here. At this instant of time, what happens? So if you observe the cathode voltage, this is the anode and this is the cathode of the diode. If you observe the cathode voltage, it will be equal to EM, right? As you can see here, from here onwards, the provided input for this diode D1, as you can see here, it is going on decreasing like this. It is going on decreasing. That means from EM, it is slowly decreasing its value. So if you observe this anode voltage here, so it will be less than EM. That is a peak value. So here the value of anode of this diode voltage is EM less than EM. And if you observe the cathode voltage, which is held constant by this capacitor, which is under charging mode, which will be equal to EM. As you can see here, the cathode voltage value is EM and anode voltage value is less than EM. Okay. Whenever the cathode voltage is higher when compared with anode voltage, what happens to the diode? Diode will be reverse bias. Whenever diode is reverse bias, this capacitor, it starts discharging. So that's why here, as you can see here, from here onwards, the capacitor starts discharging like this. So it will be discharged in this manner up to here. So once again, if you observe the anode voltage and cathode voltages, as you can see here, the anode voltage, as you can see, it is going in this direction, but here the cathode voltage is fixed at this value. If you observe the anode voltage, it is increasing and the cathode voltage is held constant. Okay, in this way the anode voltage will be going. So that's why once again what happens to the diode D1? It will be forward bias. So once again if you observe here, the capacitor starts. So like this, if you observe this figure, you can see here. So here it starts charging whenever the diode D1 is forward bias. From here onwards, what happens? The diode is reverse bias. That's why it starts discharging in this manner up to here. So if you observe the voltages at anode and cathode, anode voltage is higher. That's why the diode D1 will be forward bias. Once again, the capacitor starts charging. So at this instant, what happens? Once again, if you observe the anode and cathode voltage of diode D1, the cathode voltage is higher when compared with anode voltage. So that's why once again it discharges. So finally, if you observe the capacitor voltage will be like this. It is in the form of a triangle like this, as you can see here, like a ripple. This part I can call as a ripple, which is sitting over a DC level. From here to here, it is VDC, DC level. Okay. So finally, the operation is the capacitor voltage will be looking like this in the form of a triangular waveform. Okay, this is about the operation. In the operation, in a simplified manner, I can say that during the positive half cycle, D1 will be forward bias and the capacitor starts charging in order to reach the peak value. At this instant of time, what happens here is the provided input to the diode D1 goes on decreasing, and if you observe the voltages at anode and cathode of this diode, anode voltage is lower when compared with cathode voltage. So that's why D1 will be reverse bias. So whenever it is reverse bias, capacitor starts discharging from the peak value EM. So in this manner. So at this instant of time, once again, if we check the voltage at diode D1, anode voltage is higher. As you can see, it is going in a higher manner, and cathode voltage will be lower. That's why charging once again the capacitor charges in order to reach the peak value. And if up to here, once again, here if you observe, it starts discharging. Why? Because cathode voltage is higher when compared with anode voltage of diode D1. So these about the operation. Finally, if you observe the output voltage will be looking like this, a triangular waveform which is shifted to a DC level. Okay. So next is about the derivation of ripple factor. The ripple factor decides the performance of a filter. Whenever the ripple factor value is smaller, we can say that the particular filter is a best one. Suppose if you take two filters, one filter with a higher value and one filter with a lower value of ripple factor, the filter with a lower value of ripple factor is the best one. Okay, so that's why here we are deriving the ripple factor of a capacitive filter, full wave rectifier with a capacitive filter, right? So if you observe this waveform, you can conclude some conclusions here. Like as you can see here, this is a cut-in point. Cut-in point means it is a instant of time at which the diode starts charging. Okay, and this is called as a cutout point. Cutout point means it is the point from which the capacitor starts discharging. It stops charging and it starts discharging. Okay, and here as you can see here, so from here to here, this is called as a discharging time. Okay, so from charged peak value, it is discharging in this manner. So this particular time period is called as a T2. T2 is related with the discharging time of capacitor whenever diode D1 is reverse bias. And here as you can see here, this is called as the charging time constant. So T1 and T2. T1 and T2 will be equal to T by 2. Okay. So it happens only in one of the half cycle like this. As you can see here, it is a full wave rectifier. The pulsating DC will be like this. Okay, 0 to pi, pi to 2 pi. So this charging and discharging happens in one half cycle. Either it may be 0 to pi or pi to 2 pi. So that's why here T1 plus T2 is equal to T by 2. So this total time period is capital T. Okay, and here positive half cycle T by 2 and negative half cycle T by 2. Okay, so that's why total time period is T, and this charging and discharging of the capacitor happens in half of the cycle. That's why T1 plus T2 must be equal to T by 2. Okay, and here as you can see, a triangular shape of waveform is developed in a DC shifted manner. So this I am calling it as a VR peak to peak from here to here. Okay, VR peak to peak, RMS value of peak to peak, VR peak to peak. Okay, so by this given data, let us move to the derivation part. So in the charging path of the capacitor, it is losing its energy, and in the discharging path, it is losing its energy. One is acquiring energy happens whenever it is forward bias, and a losing of energy happens whenever it is reverse bias. That's why here the charge it has acquired is equal to Q is equal to CV. Q is equal to CV. So VR peak to peak, which is the amplitude of this particular ripple. I am calling it as a VR peak to peak from here to here. And C is the capacitance of the capacitor, and the charge it has lost during the discharge path T2, time period T2 into current IDC. Okay, so this happens like this. How we get this equation means, as you can see, I is equal to dq by dt, the equation, and q is equal to integral I into dt, and here I am taking the discharging time. That's why the limits are 0 to T2. So that's why we'll be getting IDC into T2. So that's why same thing I wrote here, IDC into T2. So charge acquired must be equal to charge last. So that's why VR peak to peak into C is equal to IDC into T2. Okay. So if you observe this diagram, charging and discharging, as you can see here, the discharging time is very large when compared with the charging time T1. Okay, it takes so much of time whenever it is in the discharging manner. So that's why here T2 is very larger when compared with T1. We can ignore T1 when compared with T2. So that's why here you know the relation that T1 plus T2 is equal to T by 2. Okay, so when compared with T2, T1 can be ignored. So that's why here I am writing T2 is equal to T by 2 by this equation. So T is equal to 1 by F. So that is equal to 1 by 2F. Okay. And here by going for this equation, VR peak to peak is equal to IDC into T2 by C, where T2 is equal to 1 by 2F. So you'll be getting this equation. VR peak to peak is equal to IDC by 2FC. And if you observe the ripple here, which is looking like a triangular waveform, if you write the equation here, we can write that equation as VR peak to peak by 2 root 3. Okay. So the RMS value of this ripple, this is a ripple which is shifted over a DC level. If I write the equation RMS value of this particular ripple, I can write the equation like this. VR peak to peak by 2 root 3. VR peak to peak means this value from here to here, VR peak to peak. So that's why here I can write the equation like this. V RMS value of this particular ripple can be written as VR RMS is equal to VR peak to peak by 2 root 3. So if you substitute the value of VR peak to peak here, we can write like this. VR RMS is equal to VR peak to peak by 2 root 3. So VR peak to peak is equal to IDC by 2 FC. So you'll be getting IDC by 4 root 3 FC. So this can be written as I am writing this IDC as VDC by load resistance RL. So same thing here. Instead of IDC, I wrote VDC by this RL. Okay. So IDC is equal to VDC by RL. Say, taking that relation, I wrote this equation. So the ripple factor is equal to VAC by VDC, or in other words, we can call it as RMS value of AC voltage by DC voltage. Okay. So VR RMS is equal to VDC by 4 root 3 FC into RL by VDC. So here VDC is there and VDC will be cancelled and you will be getting 1 by 4 root 3 FC RL. So finally this is the ripple factor of the capacitive filter. So by this particular relation, our main aim must be we need to minimize the ripple factor. When you are minimizing the ripple factor, the filter functioning will be perfect. Okay. So that's why here how to minimize the filter here. As you can see here, the ripple factor is inversely proportional to the load resistance RL. That is one relation, and it is inversely proportional to the capacitance of the capacitive filter. Okay. So ripple factor is inversely proportional to load resistance RL and it is inversely proportional to the capacitance of the capacitor. So how to minimize the ripple factor here? One option is I need to increase the value of load resistance RL, and second option is I need to increase the capacitance of the capacitor. If you increase the load resistance RL value and if you increase the capacitance of capacitive filter, we can minimize the ripple factor. Okay, that is the concluding statement. Okay, this is about the derivation of ripple factor, and let us work out for one example related with this particular ripple factor formula. As you know, the ripple factor formula is this one: tau is equal to 1 by 4 root 3 F into C into RL, where F is the frequency and C is the capacitance of the capacitive filter and RL is the load resistance value. Okay, so this is a given formula. So the problem goes on like this: calculate the value of capacitance to use in a capacitive filter connected to a full wave rectifier operating at a standard aircraft power frequency of 400 Hz if the ripple factor is 10% for a load of 500 ohms. Okay, so it is not 10%, it is 1%. Okay, so what are the given values? What is the data given here? Standard aircraft power frequency had given. What is the value of frequency? F is equal to 400 H, right? And what is the ripple factor value he had given? 1% means 1 by 100, you will be getting 0.01. This is the value of the ripple factor. And what is the load value? Load value means RL. RL is given as 500 ohms. So the given data is F is given, ripple factor value is given, and load resistance RL is given. Okay, what is the formula here? Tau is equal to 1 by 4 root 3 F into C into RL. So F is given, RL is given, and the ripple factor tau is given. So you need to calculate the value of C. Okay, so tau is equal to 0.01, 1 by 4 root 3, F is equal to 400 H. Okay, C unknown, and RL is equal to 500 ohms. So if you go for the calculation, you will be getting the capacitance value as 72.2 microfarads. Okay. So with this, I conclude my video lecture. Thank you.